Welcome to Math Muscle. Mr. D here, just checking in with some calculus and determining points of inflection and intervals of concavity for a given polynomial function. This particular question was taken from the McGraw-Hill Ryerson chapter 3, page 204. So shout out to McGraw-Hill for providing this question. So when we're looking for points of inflection and intervals of concavity, we're going to have to find the second derivative and set it equal to 0. So in this case here, because we have a function whose first derivative ends up being 4x cubed minus 6x squared minus 24x based on the original function using the power rule in each of these terms. That's the first derivative. But we need the second derivative for points of inflection, and we're going to set that equal to 0. So in other words, 12x squared negative 6 times 2 is negative 12x, and then negative 24. Set that equal to 0. And you may have noticed already that we have common factors of 12 in each of these three terms, the greatest common factor, that is. So we're dividing every single term on both sides by 12, and that simplifies the quadratic that we're solving. At this point here, we have two options. We can factor if possible or use the quadratic formula. But this one's factorable using the product sum method. The product of two factors must multiply to negative 2. The sum must be negative 1. And that's how we came up with these particular values of negative 2 and positive 1. Solving, we get x equals 2 and x equals negative 1. Now, those there are points of inflection or potential points of inflection. So by finding the intervals of concavity, we'll be able to determine whether or not they are inflection points. So we're going to use the sign diagram. We're going to substitute those values in for the sign diagram, and then using test points in each of those particular intervals and substituting those values. In this case here, negative 2, pick the value of 0 and the value of 3 for this particular interval here to the right. Substitute them into the second derivative, and really what we're interested in, so we're using the second derivative function here, the original one, not the simplified one, but the original one. What we're interested in is whether the values are positive or negative, not so much the actual numerical value, but more or less whether they're positive or negative. And I've already gone ahead and entered those values, positive, negative, and positive. Once we have that, then we can discern what the original function is doing. So when the second derivative is positive, then we know the original function is concave up, sort of like a smiley face. And then when the second derivative is negative, we have concavity downward, which is like a little frowny face. And then similarly, concave up is a smiley. So from there, we know that we have inflection points at negative 1 and 2 because there's a change in concavity. So concavity changes at x equals negative 1 and x equals 2 as per the sign diagram as we just went through. And then we have to substitute in those particular values into the original function to come up with the actual coordinates. So the points of inflection are negative 1, comma negative 6, and 2, comma negative 45. And then the question went on to ask the intervals of concavity. So then again, that's where the sign diagram comes in handy. Excuse me. So we have concave up in two particular intervals from negative infinity to negative 1, or from positive 2 to positive infinity. So I've just gone ahead and documented that using bracket notation for the intervals. And similarly, negative or concave down from negative 1 comma 2 in between that interval. Thanks for watching Math Muscle. Make sure you click subscribe and tell your friends all about it.